Testing. Testing. Sorry guys. Directly the apa? Zoom us actually directly close just now because it reached 40 minutes. So let's continue. I was in the middle of explaining. Okay. So everybody in okay. So let's start again. I think from here we stop at this point. So from here is that okay, write it taking the Laplace transform, then write it out. You will get LC VC LC actually VC squared S plus VCS VC plus VC here equal to VS. Then you take it out, make it into transfer function of VC over VS. Since the question asks you to get what is VC over VS. So rearrange it, you will get 1 over LC over S squared plus R over LS plus LC. So from here is that you can draw out the block diagram. Okay, this will be the transfer function. What's the output? The output will be VC and the input will be VS. Okay. So in contrast is that this one is using the time domain. Now we are going to use the impedance Z value. So impedance Z, this one I took it from the table in page 7 just now, slide 7. So if you have capacitor, you write it out directly as 1 over CS. This one is in the Laplace transform already. A resistor is R and inductance LS. So just write it out at the side here, LS, R, and 1 over CS. Okay. So from here is that you can write out what is VC. VC equal to IS times 1 over CS. Okay. And this will be the equation. This is the general equation. So sum of impedance. Okay, sum of impedance. So if you have the loop, in one loop is that you have sum of impedance. You have RLC. So what is the sum of impedance? Times IS. So the current, okay, in that loop equal to sum of applied voltage. So sum of applied voltage. So by looking at this is that you can write out the equation. So sum of impedance. What do you see here? What impedance do you see? We have inductance, resistance, and capacitance. Okay. So LS plus R plus 1 over CS. Okay. In bracket. Okay. IS equivalent to sum of applied voltage. So applied voltage you have only one, go to VS. So solving for 1S over VS, you can write it out as 1 IS over VS equal to 1 over LS plus R plus 1 over CS. Therefore, if you write it out, you can actually get this one VS, change it into here, then rewrite it again to get what is VC over V. You will get 1 over LC over S squared and so on. Okay, and this equation is exactly the same as the previous equation in slide number 16. So in system dynamic is that you're going to use the impedance Z to actually calculate the transfer function. Right? So let's do another example of having multiple loops. So you have loop 1, I1, which is current I1, okay, and current I2. Right? Okay, this one is the equation actually. Okay, so what you can do is that first, using this impedance, write out what is the capacitance, 1 over CS, R and LS. So you have R, you have L, and then you have C. So draw it out like this. So you have R1, you have LS, R2, and 1 over CS. Now you can start writing the equation. Okay, so look at here. Okay, so first loop. Okay, R1, I1 plus LS, IS squared minus SL, LS, I2 equal to V1. So actually, for this equation, is referring to this first general equation. So means that to get the first equation I1 is sum of impedance around mesh 1. So sum of impedance around mesh 1 times I1. So you have I1 going through this circuit. Okay. Minus sum of impedance common to the two mesh. Okay. So means that you have two mesh here. Okay. So what is common? Which is LS. So minus LS. That's why you have minus LS here. Times I2. So the another mesh next to I1, I2, equivalent to sum of applied voltage around mesh 1. So mesh 1 refer back to mesh 1. Do we have any applied voltage? Yes, we have VS. So that's why you get the first equation. Okay. Similarly, to get equation number 2 around mesh 2 is that by using the same method. Okay. So let's do first one. Okay. I'm going to go to this one first. So sum of impedance around mesh 2. So you have R2 plus R2I2 plus 1 over CS. We have this one. Okay. And then minus sum of impedance, okay, around L2. Sorry, this one, minus LS times the common to L2. You have LS times I1 equivalent to 0. Do you have any sum of voltage around mesh 2? Here, any voltage? No. So that's why you have 0. So when you write out again, you will get this equation 1 and 2, and you can rewrite it to this. We rewrite it according to this general equation. So you have I1, I2, and then I2 and I2 equal to the voltage at the side here. Reason why is that we are going to calculate for I2 over VS. We have not finished yet. We are only getting the equation around each match. Okay. So from here is that, okay, we continue. We are going to use Cramer's rule. Okay, everyone heard of Cramer's rule, right? You have learned it before. How to calculate or get a transfer function where we have more than one variable. So for the case of here is that you have I1 and I2. Okay, so we are going to use Cramer's rule. Okay, you want to get what is I2 over VS. Okay, so for this is that we are going to refer to the whiteboard first. Okay, I'm going to show to you the concept of Cramer's rule. Okay, so double click on my webcam. Double click so that it's full screen. Okay, have you write out this equation?
Yes.
Already, everyone, Heba, Zanzame, Kugan?
Yes.
Already write this?
Yeah. Yep. Done.
This one is not actually the same as what I have shown you in the slide, slide 19. It's actually a general equation in mathematics. Okay, in mathematics, you are given 3 different equations. Okay, so 3 different equations. Right. Your first equation is x plus 2z equal to 9. So imagine that actually x and y here is the value for I1 and I2. Okay, imagine that is the value. So you have x plus 2z equal to 9. Then you have the second equation. Okay, nampak tak saya? Okay. And then you have the second equation, 2z plus z equal to 9. And then you have the third equation for x minus y equal to minus 2. Okay, minus 2. So from here is that you're going to write out again into the state space value, okay, in this form. So this form is actually similar to what I shown you here. Okay, here it's the same form. You group it together, but under I2, I1, and I2 equal to the voltage at the end here. Okay, so group it together. So actually, you have this value is x, y, and z, and this is the value for in case of value voltage. Okay, so this is how you are going to actually get the value for x. Okay, if you're given 3 value, how to find x? Okay, we are going to use Cramer's rule. So x is actually determinant of x over d determinant. Y is determinant of y over d, and z is determinant of z over d. So what does it mean? First is that you need to get determinant. Determinant, how do you get it? It's based on the original equation here. Okay, determinant. So based on d, how remember how to get determinant? D.
Yeah.
Can you remember? Okay, start with 1. Okay, 1, 2, 1, minus 3, 0. Okay, minus 0, 0, 1, 4, 0, plus 2, 0, 2, 4, minus 3. Okay, so you will get what? 1 times 2, 0 minus 3, you get 3. Okay, minus 0, plus 2, 0, 0, minus 8. So you get minus 4. Okay, is it correct? 0, 4, 4 times 2, 8 times 2.
16. 16.
Okay, 16, So you get 13, minus 13. Okay, so this one is the first concept. So this is how to find the determinant. Okay, how to find it is that start with 1, take 1 here, 1, close this x value, so you get this 1, 2, 1, minus 3, 0. So that's why I write this down. 0, 0, 1, 4, 0. That's why you get it. Okay, everyone. And then next is that plus 2, 0, 2, 4, minus 3. So then you get this one. So calculate, you get minus 13. Okay, so right now you have actually settled halfway through. You get what is the value determinant. Okay, now we are going to get the value for the x. The x. So how to write for the x? Okay, to calculate for the x. The x is by actually getting the value of the x. You know x. X is here. Okay, this value insert 982 of the right side, right hand side, yeah. So that's why I write 98 minus 2, and the rest is copy from the original equation. So you have 0, 2, 2, 1, minus 3, 0. So this one. So write 982 minus 2, and then the rest is the same. Transfer to this. Okay, how to calculate for the x is similar like calculating determinant just now. Okay, so I just fast forward. You will get the x equivalent to dx equal to minus 30. Okay, you can try it out later on. So let's just do very quickly how to get dy. So dy is 98 minus 2 is you substitute at the y part, 98 minus 2. So the rest is the same as the original here. So you have 1, 0, 4. And you have 2, 1, 0. Okay. So you will get minus 26. Okay. Okay. Can you see the bottom here? Can you see it?
Yeah.
Yes.
If not, I will write here.
Yes.
D, Z. What is that? Take 98 minus 2 at the Z part, 98 minus 2. The rest copy the original. 1, 0, 0, 2, 4 minus 3. So dz minus 52. So right now you can actually find or calculate for x, y, and z. Okay, so very simple. So x, the x is minus 15 over minus 15, so you get what? Okay. Anyone talking? No, okay. So dy is y is dy over d. So we have minus 22 minus 26 over minus 13. So you actually get okay. Dz is minus 15 over minus, you get 4. Right? So by understanding the concept of Kramer rule, I think after this you can do any exercises lah to understand the concept. Okay. So right now is that the question is that to actually calculate for IS over VS. So where was IS just now? The second value here. Okay. So IS. So imagine you have I1 plus I2, this value. Total voltage value here, voltage. Okay. I2 because you have this two equation just now. I2 go to the voltage value. So equation 1 and equation 2. The question was to find what is I2. So I2 is what? Same concept. So means that D I over D. Okay? Follow me? You can follow me, right? So that's why for the Kramer's rule, if you see here, I2 is actually equivalent to, okay, you take out the value for this determinant. So the upper part is actually D I2. Okay, D I2, which is, that's why the second value here, you substitute with this VS0. Okay, and the first value is you take this value. Okay, R1 plus AS. So this is the determinant that you find here. Okay, just now. So that's why I2 you will get this equation, and you see this is determinant. I2 you get, substitute here, you will get in the end I2 over V. I2 you get this value, so take it out, you will get I2 over V, you get this equation. So this one will be the transfer function for the system. Okay, so try to do it at home. Try to, from this step, try to do get what is I2 value and substitute I2 value into this equation and just prove this equation is correct. Okay, everybody okay? Everybody okay? Okay, I think okay, for this one SLT, you try to do at home. This is actually similar to what I have shown you for two loop system. So this is 3 loop, same thing. Okay, how to get the equation is that do at home. I'm just going to explain it. Okay, the first match equation is that get this one. So sum of impedance around this. Okay, so that's why you get sum of impedance times 1 I1S minus sum of impedance 2 common to I2. So I2 nya what is common? It's actually this one. Okay, and minus another, because you have another loop which is I3. So minus, still minus here, sum of the equation. So you have 1 only. Okay, equivalent to any voltage around this loop, you have Vs. So you get the first equation. Okay. Second one is, okay, to get the mesh for second equation, same method. Okay, we are going to refer to this one as the main reference. So first get this one, sum of impedance around mesh 2. So you have the inductance. You have the inductance 4, 3, 2, and then resistance, and then minus impedance common to I1. Okay, common to I1. So means that this one. So there are two impedance that's common. Okay, and then minus I3. So what is common to I2? It's only impedance 4S. Okay, equivalent to sum of applied voltage. Any voltage around I2? No. So it's equal to 0. So write that out. You get second equation. Third one is that you're going to get the equation around I3. Okay, same concept lah. Okay, get first around here what is common to I3, I1, and I2, and then equal to 0. Okay, and then after that, okay, the question, okay, but the question was do not solve it. They didn't ask find what is VC over VS. No, they didn't ask that. So right, but do not solve the mesh equation. So come out only with the equation, the three equation. Okay. This one is another example. Do it at home. Okay. SLT is during learning time. So find the transfer function. This one is given. Find the transfer function VC over VS. So what is VC? VC is over here. So if you remember that, how to get this one is that just get the equation. So and for this exercise is that assume that whatever value 1 over R and 1 over R2, just substitute it to G1 and G2, because if not, it will be so complicated. Okay, substitute it. Okay, so try to prove that you can get this equation. Any question before we go for electric motor? Okay, so next we go for the electric DC motor transfer function. So for this is an example of a DC motor, electromechanical system, amateur control DC motor. So you have, if you see here, this is actually what you have learned just now on electric circuit. Okay, but it's connected to a motor. Okay, and then later on this motor, so you are going to actually model this. Okay, and we are going to model this as a block diagram like this. So you have GS. EA, this is EA is the input, means the input armature current, okay, and the output is the degree, the angle, theta M. Okay, so GS is actually whatever is inside here, include the circuit, including the rotor. Rotor is including rotor damper. Everything is actually what you have learned in mechanical mechanical modeling. Okay. So let's look at this example. You can refer to control 9 for these references. Okay, so a magnetic field is developed by stationary permanent magnets or a stationary electromagnet called fixed field. Okay, basically, if you have a rotary motor, rotor is moving in rotary motion. So normally you have a permanent magnet or a current through the coils. So that's why if you see here is that you have fixed field. Fixed field means that you have the permanent magnet. Okay, and for station, which is we call it as the this one a fixed field. And for the armature current is rotary is when you have a current flow through the magnetic field. Means that current flow through the coils, and therefore it will actually actually produce the magnetic field. So how to calculate that is that you have F, A force, if equal to B. B is the magnetic field strength, okay, times I, length of the conductor, means that you have your coil conductor, length of the conductor, times IA. IA is actually the armature current. Okay, so we take it as equation 8 lah. Okay, this one I took it from my previous class when I was teaching electromechanical system undergraduates. So actually it have a few example in the previous one, but it was actually mechanical dynamics. So now we start with equation 9. Okay, so next is from here is okay. The output torque turns the rotor, so means that the output torque here will turn the rotor, rotating member of the motor means that is going to turn the rotor. The conductor moving at the right angle to the magnetic field generate voltage at terminal conductor E equal to B LV. So E is the voltage here, VB. Okay. Okay, magnetic field strength, B length of conductor, and V the voltage. So you can get this one, which is second equation, E equal to B LV. Okay. And next is that since the current carrying armature is rotating in magnetic field, okay, its voltage is proportional to speed. Okay, back, which we call it as the back EMF field. So VB here. Okay, so we can actually write out the equation VB equal to KB, the back EMF constant, dot d theta m over dt. Theta m is actually the output of the motor. Okay. Doing Laplace transform, you get VB equal to KB as theta m. So this one will be equation 11. Okay. So now you are going to write out the equation. So the relationship between armature current, IA, applied armature voltage, ET. Okay. And then the back EMF, VB. Okay. Back EMF is actually the force or voltage that is actually the opposite of the EA value. So you have like a friction force. When you have a normal force, you have the friction force. So that one is the back EMF for a electromechanical system. So based on that, you can write out the equation here using the circuit theory just now. So we have RA IA plus LA SIA, okay, plus VB equal to IA. So you get the 12 equation number 12. Okay. Developed torque by motor is proportional to armature current. So ignoring TF. What is TF? TF is actually the torque, friction torque. Okay. Like mass, a mechanical system, you have friction also for torque value. But here is that we are going to ignore TF. TF is equal to 0. So by having that is that we can write the equation torque of the motor equal to KT. Okay, what is KT? KT is the torque constant times IA, which is armature current. Right? So if you see here, this one is the original equation for torque lah. Torque is equal to KT IA minus TF. So you have you need to, in reality is that you need to minus the friction torque, or for mass is that you have the friction force. So normally when we do the modeling, we omit this unless you need to do some experimental work to find out what is the friction torque. Okay, by adding load cell, okay, to the system, try to do an open loop, find out what is the friction torque or friction force value. Okay, so based on that is that, okay, I write out again the equation in this page. So you have equation 11, VB equal to KB as theta M, and then equation 13, torque of the motor equal to KT IA, and then the 12th equation is actually the circuit for the single loop. Okay, rearrange equation 13 here, you will get IA equal to 1 over KTTM. Okay, now we are going to substitute. Okay, to find the transfer function is that substitute 1 and 14, 1, 11 and 14 into equation 12. Okay, means that substitute this to this equation. So you will get this transfer function. Okay, so in the form of Tm, theta m, and EA. The question just now was get the transfer function of EA over the output, the input over the output over EA, right? So output is theta m over EA. So you have this one, theta m is output, EA is the input. Okay, so this one is the transfer function. Okay, so let's look again from this equation is that you know that we can write it into this plot diagram. GS, theta M is output, EA is the input. So, and normally this one, you can actually draw it into this block diagram equivalent. Okay, so you have inertia, you have damping value, and then you have torque and theta M value here. Okay, so JM is the equivalent inertia of the armature, which includes armature inertia. Okay, and DM is the viscous damping of the armature. So you know that when you have the rotor, everything, rotor is connected to bearings at each end. So that bearing have damping value. So that's why DM in this value is, you see that we have the damping value. Okay, so we continue here. Okay, if example, this equation, we connect it to the damping value here. Okay, so equation 15, continue from here. Okay, so from the free body diagram is that this equation, okay, we connect to a mass at the end. So the rotor, imagine the rotor just now, we connect it to a mass that is going to rotate a mass. Okay, rotor, we connect to a wheel. So the wheel will be the mass. Okay, so this one, we get the free body diagram. You have learned this yesterday. So Tm equal to Jm s squared plus Dm theta m, equation 13. Substitute 15 and 16 together, and you will get the equation for the transfer function. Okay, so you get EA, theta m, and theta m here. So, and if you assume that the armature inductance LA is too small, okay, and RA is used for DC motor, so when you rearrange it, you will get this equation. Okay, LA normally is too small compared to RA, so that we assume that it's 0. So write out again, you get this equation. Okay, remember this is the output, this is the input, and then you rearrange it, become theta m over EA, then you will get this transfer function. Okay, so theta m over EA is actually the transfer function of this one is the transfer function of the system. This whole thing is actually GS here. GS here. Okay. And if you look at this equation, if you look at it, it's actually represent K value. This is the whole thing, K value. You have S plus this whole thing is actually alpha, a value lah, because you know that if you have, you know what is the value KB, KT, this is a constant value. KT, KB is a constant value. And then RA the resistance, and DM is the damping. So you can actually get a value here. Okay, this one you can actually calculate it. Okay, and from this one will be the final transfer function. Later, during the modeling for MATLAB and Simulink, okay, you're going to draw the plot diagram. So assume that, okay, we take equation 13, 16, and 12 from the previous slide. Okay, so you have equation 13, 16, and 12. So rewrite the equation. So let's look at the color coding. Okay, first let's look at this purple. Okay, block. Okay, you have Tm equal to Jm s squared plus Dm as theta m. So draw out like this. Okay, input output. What is the output just now? What's the output? Theta. Theta. And the input is EA. So right now we want to get what is theta. Okay, so this equation, take theta as the equation value. Okay, theta m is equal to, rewrite it, equal to 1 over JMS plus BM times torque. So if you rewrite this, you can actually draw the block diagram here. So that's why you draw the first block diagram here. Okay, so theta m, block diagram, the value is 1 over JMS plus BM times torque, input to the system. Okay, so first block done. Second one is that we are going to find what is TS value. So TS, where is TS?